Welcome to Kinematics. Let's get started. So for projectile motion, we see this in everyday life. We throw balls in the air, something's flying in the air, something's being knocked. But if you look at the ball's trajectory, it happens in a nice quadratic equation. And that is because of gravity. When a ball is moving upwards, it has an initial velocity. And then as it goes up, because the acceleration is pointing in the opposite direction, the velocity slows down and then it stops in the y direction at the top. And as it comes back down, it's filling this pool from acceleration, which starts accelerating it downwards. Now the interesting thing is at the top of this trajectory, the velocity in the y direction is 0. But that doesn't mean the velocity in the x direction is 0. Remember, there is no acceleration in the x direction. So therefore, the velocity in the x direction is going to stay constant throughout this whole process because there is no external acceleration in the x direction. It's a very key component. So at the top of this trajectory, there is actually a velocity, but it's all in the x direction, and none will be in the y. So when we start looking at projectile problems, it is very important to break down our velocity into components. That is the first step in a projectile problem, is to break it down. Now you might not know what theta is, or you might not know what your initial velocity is, but you do know that your x component is going to be your initial velocity times this cosine of theta, assuming you're taking the theta from the x-axis. And that your initial y component is going to be sine theta. You can use this to help solve future problems by applying those kinematic equations in the previous slide. You also know that with projectile motion that the acceleration in the x direction is 0 and the acceleration in the y direction is negative g. This is also very important that you can put this in your problem. So you already know your initial velocity is going to be broken up into two components. And you also know that your acceleration in the x direction and the y direction. That helps with when you're solving these problems to write those down. You also know that at the top of the trajectory that you're only going to have a velocity in the x direction. Think about it this way. How else is this ball going to keep on moving in the x direction? If you suddenly have 0 velocity at the top of this trajectory, this ball won't keep on moving in the x direction. It would just start falling straight down, and your trajectory would look kaput. And that's not what happens. We see this nice parabola. That's because the x direction has no acceleration acting on it, and therefore it's going to stay constant throughout that trajectory. So if we assumed that our initial velocity was a 9.8 in the meters per second in the x direction and a 19.6 meters per second in the y direction, we can use this information to help solve our case. One, you already know what's happening in the x and y. You could actually solve for the theta because you know your values in the for the x and y components of the initial velocity. You also know the acceleration is going to be equal to 0 I hat minus 9.8 j hat meters per second squared. And so using these information, this can help you actually figure out how high the ball was thrown. You could figure out how long it takes to complete till it falls back on the ground, or when it gets to the peak, or any other part. You can even figure out what the time or location is of that ball at some random point. Now, if you have two balls and you drop a ball and you push a ball off the cliff, it will actually hit the ground at the same time. Now this is assuming that you only have a horizontal velocity when it rolls off that cliff or is pushed off that cliff. If there are any y components to that initial velocity, then that is going to change the time it takes for it to hit the ground. But if you have a pure horizontal velocity and your velocity in the y direction is equal to 0, there is no difference there than if you had just dropped a ball, because here your initial velocity is equal to 0. Now you don't have an x component, of course not, but if you look at the equation that you would use for time, that one you don't necessarily need an x component to find either to figure out time, because both situations would have a change in y is equal to your initial velocity in the y times that change in time minus 1/2 g change in time squared. As you can see, to figure out the amount of time that it would take to fall, all you need is the acceleration in the y direction, the initial velocity in the y direction, and that change in the y distance. So look at this question. What do you think would be the answer? You can pause the video to think about it. As you can see here, they hit at the same time. They are both falling from rest. The heavy red ball is falling from rest at 2 meters, and the yellow ball is being fired horizontally at 3 meters per second at the same height. That 3 meters per second actually does not contribute to calculating that time. Now you can use it. You might not know that change in y, and therefore you might have to figure out time using the horizontal value, but they're both falling the same y distance with the same initial y value. So therefore, and with the same acceleration. And so therefore, it should take the same amount of time. Try this problem. You may pause the video if you like to think about it. So unfortunately, my red arrows do not show up in the right spots, but you have a 100-gram ball that rolls off a table and hits 2 meters from the base of the table. And then you have a 200-gram ball that rolls off the same table with the same speed, and it lands at a distance. Now what distance will that be? Does the mass change how far that ball goes? No, because the important thing about the x direction is the speed, and if they both have the same speed and they're traveling the same y distance, they will land at the same distance. Think about it this way. If we didn't have gravity, if we threw a ball or kicked a ball, it would never come back. So it has to come back. It has to fall. And if you look at that difference between the actual trajectory and the trajectory without gravity, you actually get this minus 1/2 gt squared component. That's another way to think about it. You can also plan this out. You may know from experience if you've done any kind of bow and arrow training, or maybe you go to a firing range, or just playing with friends. You can actually time, if you look at an object that's falling, you can figure out if you throw your arrow at the same time that that object it drops, it will hit. And that's assuming that you shoot the arrow at that object. Because if you do it at the instant that you release, that arrow will end up also falling to the same amount that the coconut or any kind of thing that's falling falls at. Now you may say, well, what happens if you have a gun? Well, yes, the gun travels a lot faster. So it's going to get up there at a faster time, meaning the coconut will not have fallen that much. So yes, it's going to follow that trajectory too. This is one reason why we do not fire our guns willy-nilly into space, because it actually can come back down and hurt somebody and kills a random person. And it has happened to people before. So make sure if you're doing any target practicing, that whatever this object that you're using is accountable and not somewhere free flying around that could hurt somebody. Now, you can actually look through these range. Now, this equation only works if your initial position is equal to your final position. That's the only time when this equation works. But you can use it to figure out how you can get the max range when you hit a ball. And it turns out the max range is indicated by your speed, but if you fired a bunch of balls with the same amount of speed at different angles, it turns out you'll get the maximum range when you're at 45 degrees. This shouldn't be that surprising, but nonetheless, 45 degrees hits the max range. The minimum range is going to be anything that's less than 75 degrees, as you can see. This is also very important if you plan to play soccer or any other games, as this will be important. So, if you have a projectile, 1 and 2, are launched over level ground with the same speed but at different angles, which one do you think will hit first? Let me give you a second to think about it. If you said the second projectile, you are correct. If you're wondering how in the world could you figure that out without more information than that, think about free fall. Break these trajectories in half. Which one, when it's at the peak, will take longer to fall? It's going to take a lot longer to fall the distance from the peak to the ground for projectile 1 than it is for projectile 2. Projectile 2 is half the height, and we know that if we assume that our velocity y is equal to 0 at the peak, which it is, and we just look at that snapshot of that last half, then we know that that change in y is equal to 1/2 gt squared. And yes, there is a negative sign here, so you can just put a negative here because your change in y is actually negative. But as you can see here, that this change in y is directly that time is directly impacted by that change in y. So that's going to affect how much it's going to fall. Now you may say, well, what about the beginning half? Well, look at these parabolas, they're symmetric. The amount of time it takes to fall from the peak to the ground is the same amount of time as it takes to go from the ground to the peak. What happens if we launch at different speeds, but we have different speeds, but then instead we launch them so that they hit the same height? Which one is going to hit first? Projectile 1, projectile 2. Think about it. If you say they hit the same time, you are correct, because they are falling from the same height. So even though projectile 2 has more of a velocity in the x direction than projectile 1, the only thing that will affect is the range that projectile 1 will have. So in this problem, we will do this in class, but you can try it out if you like. Feel free to go ahead and try to figure out what information you can get from this problem and what you could find. This is another problem that you will be doing in your groups, along with some other. This is a more challenging problem where you have two things happening. You have something going on with the ship, and you have something happening with a projectile being fired from the tower. Feel free to play around with these two problems and see what you come up with, but we will address them in class.